Welcome back to Let's Talk Concrete, a platform where we go beyond materials and mixes to talk about how concrete is shaping the future of building and construction. In every episode, we bring you insights from industry leaders who are redefining design thinking, performance benchmarks, and structural longevity. Today, we are at episode 4, and we are diving into a topic that's becoming increasingly critical for modern infrastructure: the evolving robustness and design flexibility of structures with high grade and high performance concrete. High grade and high performance concrete are not just enabling strength, they are unlocking new design possibilities, improved durability, and smarter structural solutions. To help us unpack this evolution, we are joined by a true pioneer in this space, someone who has been instrumental in pushing the boundaries of what concrete can achieve in India. Our guest today is Dr. Satish Jain, Managing Director of UHPC India Private Limited. With over 25 years of experience in structural and construction engineering across India and the United States, Dr. Jain holds a PhD and MS in structural engineering from Iowa State University, USA, and is a licensed structural engineer in both countries. He is widely recognized as a pioneer of ultra-high performance concrete in India, having led its application in new construction, structural strengthening, impact-resistant structures, marine applications, architectural elements, and advanced engineering solutions. Dr. Jain is also credited with establishing India's first indigenous commercial UHPC premix manufacturing unit, and currently serves as chairman of the UHPC Technical Committee at the Indian Concrete Institute, and also a member of IRC Subcommittee B4.5 on UHPFRC. His work has consistently focused on performance-based design, constructability, and innovation, making him uniquely positioned to discuss how high-grade and high-performance concrete are reshaping structural robustness and design flexibility. Dr. Jain, it's a pleasure to have you on Let's Talk Concrete.
Thank you so much for having me here, Mr. Paras.
Sir, let's begin by understanding how the concrete journey evolved from 1:2:4 to 150 plus MPa. Can you guide what brought the need?
All right. So let's go back, a few decades down, right? If you look at the concrete strengths in India, we really talk about concrete in terms of M10, M15, and that's pretty much, the megapascals, which is out there. So 1:2:4 was the easiest way that they could do it in the past, right? It was just at that point cement, sand, coarse aggregate, and of course water at the end of the day. So 3 components, and thereby the 1:2:4, and that would give you a decent concrete that you can make regular structures out of. Over the years, if technology doesn't move ahead, then we are left in the old age, ancient age kind of the things. So the need started becoming, more and more. When building starts going from 4 stories to 10 stories to 20 stories to 60 stories, what do you need? You need slender columns. Imagine if I were to use very low strength concrete, then you would have a column of probably 1.2 meters by 1.2 meters, if I went for a medium rise or a high rise building. But that is not what we want today. We want columns which are much leaner, 600 by 600, 750 by 750. So the need for the column strength went up. The column sizes are really dependent on the concrete strengths. On the other aspect of it, there were other developments taking place in the concrete industry, which one of the areas is pre-stressed concrete. So when you look at pre-stressed concrete, again, you need some higher concrete strengths. So thereby the evolution started. It went from about M15 to M20 to M25, and if I were to even go back as recent as year 2000, if you were to be working with a concrete like M30 or M35, nobody wanted to go beyond that. You were being questioned as to why you have probably prescribed a M50 or a M60, because nobody wanted to pay the price for that. And today, look, we have started talking about 150 grade. Times have changed. You can engineer mega structures, leaner structures. You can give different kind of flexibility in terms of whether it's architecture or whether it is constructability. The concrete strength now counts, right? And so the history has evolved. Last 20 years have really changed, 20 to 25 years have really changed how concrete evolution has taken place. And I think that is where kudos to the material science engineers, that they have made this material compete with structural steel.
So to answer those people who are questioning this particular process to keep the costs in check, how do you silence those people who are questioning this process?
Believe it or not, the cost actually is not a factor. Yes, the UHPC that we are talking about, 150, it's actually a little bit of a different animal, let's say, right? Because it is more than concrete, it's a fibrous composite material. So let's keep that aside. But still, let's talk about concrete going as high as 70 or 80 megapascals or even 90 and 100 megapascals right over there. When you're using a high strength concrete, you're reducing the material as well. So where is the increase in cost? You're compensating, right? And when you compensate, you're compensating not just in the volume of a particular structural element, but you are also compensating by reducing the foundation sizes, by reducing the earthquake loads, because the earthquake load is really governed by the mass of the structure. So I don't think cost is a matter at all when it comes to usage of high strength concrete. It's just that engineering has to become better. The structural engineering has to become better to utilize the high grades of concrete and utilize them in variety of structures, whether it is buildings, heavy energy structures like maybe you would say induced draft cooling towers or natural draft cooling towers, or even bridges and other infrastructure projects. Yeah.
So what are the special challenges faced in designing high grade concrete?
Interesting question. Very, very interesting question. What are the challenges? So here, interestingly, when you mention grade out here, we are keeping the durability part a little bit away. Hopefully we come to that. So we're talking of two aspects in terms of the strength or the grade of the material, right? One is the chemical aspect and one is the physical aspect of the concrete, right? And we can get strength from both these parts. The chemistry aspect really talks about the reactivity of the raw materials, right? And what kind of admixtures or supplementary admixture or supplementary cementitious materials that you're using. So that is one part of it, and material science has evolved quite a bit about around it. But let's talk a little bit about the physical part of it. In terms of the physical aspects, there are two things. Number one, what kind of aggregates you're using, what's the hardness of those aggregates. So that's one part in terms of physical. The other part, which is very, very important, is what is the particle packing of the material. When I say particle packing, let's bring this into the picture. Let's give a little example out of it, right? When we talk about the physical aspects and we talk about the size of the aggregate or the particle packing of the aggregates, that matters a lot. Let's talk about extremely coarse aggregate concrete. Sometimes we make very, very lean concrete, very low strength concrete that can go in dams as well, that can go in strengthening of the subgrade of the soil as well, wherein you may be using about 300 mm aggregate size, right? Those are very low strength concrete because the voids on these concretes are very high, right? The cement slurry is very thin. Then as we start to increase upon the strength, you actually lower the size of the aggregate. So next comes where we use aggregates of 30 mm or 40 mm size, right? and then we start to mix the cement and the sand, and there is some kind of particle packing. You still have voids, but the voids, the porosity has gone down, right? But there is an increase in strength that you get. So now you have started talking about M20 concrete, maybe M25 concrete also. And then you start going, even lower on the coarse aggregate size, that is 20 mm. And this is where you start going into concretes of strengths M30, M40, M50, probably M60 as well, right? The void ratios have started coming down in the entire mix. So what's next? When you start, when you want to go to M70, M80 and M90 and M100, you got to go down further on the aggregate size, and you go to about 10 mm aggregates as the starting size. So you have 10 mm aggregate, then you have the sand, which itself is graded, and then you have the cementitious materials. So literally you're talking of this, the complexity or the challenge is not much, but it is about the science that you start putting into it. And then people have difficulty. What do you do if I want to go more than 90 or 100? 100 itself is difficult to achieve if you don't have good quality aggregates around. But realistically, what do you want to do if you want to go, more than that 90 or 100 MPa? So the beautiful part is, instead of getting that 10 MPa down further, you completely eliminate that out of the picture. And that is how you get ultra high performance concrete, is you eliminate the coarse aggregate and you start with the fine aggregate itself, and you do a very tight particle packing, so the physical part is taken care of. And so when we say challenge, the challenge is literally, one thing about the physical aspect, which is the hardness of the materials, the particle packing of the materials. And when it comes to the chemical side, yes, all the raw materials, either we use I shouldn't say either, but we should use highly reactive raw materials, plus very good admixtures that can actually, disperse all these cementitious materials very evenly into the system and provide you a robust high strength concrete.
So we left durability part. So let's discuss the durability as well with this process.
Okay. When it comes to durability, now imagine, I just mentioned the physical aspects of particle packing, right? The lesser the void, don't you think the durability will start coming down? Because water ingress would be lower, the chloride ingress would be lower. So the more and more tight the particle packing, the higher the durability. Let's go back 20 years again, 2 decades. How many people were worried about durability of concrete? If you go to a structural engineer and you look out at the specs, it used to always talk about strength, nothing more, right? But those times have gone. Today we are living in an era where, yes, strength is important, but durability is more important, right? We are looking at structures where we have started asking for 100 years service life, and when we start looking at materials like ultra high performance concrete, performance being the keyword, strength is not the keyword over there, performance being the keyword, we are asking for 100-year maintenance free life. That is the level of durability that can be achieved in today's date and time. So there has been an evolution of durability, which has happened in the past 2 decades. And all kind of chemical analyses can be done. You can do or chemical and physical analyses with respect to that. Common test being chloride migration, water permeability, chloride permeability, carbonation tests, rapid chloride penetration tests. There are a variety of tests which are available, out there today to test the durability of concrete.
So it's not a concern. Achieving durability is not a concern.
Not a concern
with today's
at
technology.
All. Yeah. It is more about exposure of the teams that are working, other than the concrete technologists, that there is something called as durability out there. They know they need it. They're worried about paying for it. But you got to make them understand that it is not necessary that they have to pay extra for it.
So we have an upper limit on maximum permissible cement content. How can we design concrete for M100 grade maintaining that?
See, again, a great question thereabout. traditionally, if you look at the Indian codes, right, we talk about compressive strength in terms of 28-day strengths of the concrete. In India, we talk about cube strengths. Certain other countries look at it in terms of cylinder strengths, but the 28-day strengths, right? Now, as we go higher and higher, one of the aspects is the cement content itself, right? But the big question is, do we really need all that strength in 28 days? When we are designing a structure, very, very important to understand, the designer has to look from that perspective. Will I need the strength in 28 days, or is it okay for me to get that strength in 56 days or 90 days or even 120 days, right? If we can answer that question, then why to add cement? There are supplementary cementitious materials like fly ash and GGBS, right, which will provide you similar reactivity but slowly over a longer period of time, right, and they are waste products. So, from a sustainability angle, that works too. So, instead of adding additional cement, you add fly ash or GGBS, and you're still able to achieve those strengths, albeit you may not get it in 28 days, you can get it in 56 days and 90 days, and you should be able to use them for your concrete production.
But it also depends on the patience level of the contractor or structural engineer.
Well, not necessarily out there, because if you're designing 100 MPa concrete, see, what the contractor is really worried about is how quickly he can strip the concrete, right? And while we are talking about normal strength concretes, you may say I need 70% out there of the strength to strip it. But when we are talking 100 MPa and all, do we really need that, is the question. So, that is where they got to communicate and sit together with the structural engineer and come to some terms, right? Is it okay if I strip when my concrete reaches 30 MPa? Now, 30 MPa can be achieved faster, right? Those kind of questions, if they are put on board, I don't think the contractor, will need to worry about anything. The structure will need 100 MPa at a later date, and that's just particularly fine. I do have to, right here point out one particular project that we did with Nuvoco way back when we provided a 80 MPa concrete, at about 90 days on a building project, and that building project was in Bandra, and that was probably the year 2012 or somewhere right around there, 11 or 12, somewhere right around there. So, when we talk about long gauge concretes, right, even as early as 2000, 2011 and 12, there was a project in Bandra which was done with your group, where M80 concrete was used at 90 days strength, right. So, where the cement contents were limited, the fly ash and the GGBS, these products actually went into the making of the concrete, and we did not need all that concrete strength up front. So, we are talking almost about 13, 14 years back. So, there is a lot that you can do just without increasing the cement content.
Right. So, at this juncture, I need to ask this question: which one is more reliable, cube strength or cylindrical strength?
That's very, very interesting question again, because the Indian codes have already been, always been set up on cube strengths. Okay. Whereas at the very fundamental, you will see that it is the cylindrical strength, right, that is used in some of the countries like the USA. But then the Indian code is set in such a way that the cylindrical strength is changed to a size of a cube, and then you can look at the cube strength. Now, where the problem comes is when the strength goes increasing, right. At lower strength, there is a ratio between the cylinder strength and the cube strengths, right? So the cylinder strengths are about 80% of the cube strengths. But if we are just doing cubes at 80 MPa, 90 MPa, 100 MPa, then you're probably trying to be over conservative in terms of your design, because the cube and the cylinder strength starts coming closer together at 100 MPa or so, right? Very close together. So that 0.8 ratio is no longer valid, correct? So in design, either you take that variability into, into your design, or you are at least not going to be, unconservative in your design if you just go ahead with it. So I'll just put it that way, that at the fundamental there is the cylinder, but there is nothing wrong with the cube strength as such.
So for a project, moving from medium grade to high grade has helped in getting slender structures like columns for high rises or using UHPC, has increased the spans for bridges, reducing the piers as well. Is this economically feasible as a total project?
So for 1 second, I'm going to keep the UHPC aside again. It's a totally different animal, like I said, and we need to treat it as a different material, not just as a concrete. But if we are talking about, going from 30 MPa to 50 MPa to 70 MPa and now, 90, 95 MPa, etc. Yes, the cost increase is definitely there. But at the same point of time, I think mentioned as before that if you are looking at a high-rise building, the carpet areas are quite important. You need to get down on the size of the columns, and that's where the high-grade concrete is really helping up and shaping up, the modern-day projects. I'll tell you that way back, as back as 2006, when I was working in the United States, and I'll tell you two different cities, right? One being Seattle and one being San Francisco or Los Angeles. So we're coming into California right over there, right? Now Seattle was very progressive, that they started using really high grade concrete in that terms, M100 and so onwards. So they were able to get very, very nice slender columns out there for use in buildings or for going long span in bridge girders, etc. Especially I'll talk about buildings a second. But when you looked at California, there was a huge resistance. Okay, why the huge resistance? Because the more high strength concrete you produce, the concrete producer were able to sell less. Okay, there was a major resistance for a long time. But you cannot stop the flow of water, right? So when high strength was already into the picture, it was only so long before that that union had to break, and high strength concrete came into perspective in California as well. So those are different kind of challenges, right?
So, but why there is no uniformity in US, like two different cities, two different kind of processes?
It's just because again, politically speaking, unions were very stronger in California and cities like San Francisco and LA, and the stronger the unions, they didn't want modern day concretes coming into play and reducing their concrete quantities. It was as simple as that. Right? There was no other reason, right? No other technical reason beyond it.
Just economics.
Just economics of volume, right? But that changed, right? And so has it in India. When I started, working in India as a consultant, I saw that picture very vividly, that people were worried about using high strength concrete. Number two, people were also worried about using anything more than a 28-day strength concrete. Today, the scenario has changed, literally changed, and we are really able to see the best use of concrete, high grade in vertical members, high grade in flexural members like beams, etc., along with pre-stressing, It has just changed the way concrete structures are coming up.
So now we have arrived at my most favorite segment, which is the Mythbuster segment. There are several myths in this industry, so I would like you to bust one of the myths for us and for our viewers. So my question goes, high-grade concrete is always durable and it makes the project expensive as well. Is it a myth, sir?
So interesting myths that go around, right? High-grade concrete is always durable. You know, those words, keywords itself are
So clickbaity. It's clickbaity.
Yeah. So I think there is no right or wrong answer to that. But I think as you know, I explained earlier some physical properties and, you know, reduction of the voids, etc. If you look at it, as the strength increases, the voids goes down. So the durability aspect, you know, keeps increasing. So in general, I would say in general, yes, the more the strength, the more the durability. But there is a reason why we just don't say high strength concrete and leave it at that. The modern day material engineering science talks about high strength, high performance concrete. So there is more that is done to increase the durability, and therefore it's not just about high strength, but it is high strength plus high performance concrete, right? So it is not just that strength increases durability, but there are several other aspects that help too. But in small ways and good ways, yes. The higher the strength, the lower probably the void ratio, and it helps to increase the durability.
So it's not a myth. But what about paisa, sir? What about investments? What about the money we are putting in to achieve that durability?
Engineering has changed. I think during the course of this wonderful talk here, we have spoken that money is looked at in the wrong way, right? You may talk about a concrete which may be 5,000 rupees, maybe M30 at 5,000 rupees, and maybe M50 or so, maybe at 7,000 rupees in Mumbai. And then you talk about something like a M90, which may be closer to 13,000, 14,000, you know, anywhere 12 to 14,000 rupees. So the cost goes up. Somebody who's just looking at 1 cubic meter this, 1 cubic meter that, and 1 cubic meter that, is generally going to raise eyebrows. They are going to raise eyebrows. But then, you know, we made the facts clear. Higher the strength, lower the volume needed. Lower the volume needed, reduction in foundations, reduction in earthquake loads, right? More space, developer is able to give more carpet area, right? There are advantages, several advantages out there. So it is more about educating about high strength, not just high strength, but how that cost variability is, you know, different. Yes, it may cost more, but does it really cost more on the project? It's a huge question mark right there.
So, sir, before wrapping up, I would like you to tell us your experience. How do you feel about this initiative, our initiative of Nuvoco? Let's talk concrete.
See, I'll tell you, wonderful. And I'll tell you wonderful for a very, very simple reason. You look at the construction industry today in India, it's booming like crazy. Every other place, if you have money, you can put up a concrete RMC plant together and sell concrete. Whether or not you have a right guy, you know, directing you towards the right quality concrete or not, but if you have money, you can put up a concrete plant and concrete is going out. It is very, very important, extremely important that the industry, whether it is people on the site, whether people who are managing the project, whether people who are designing the project, whether people who are specifying the concrete, they need to be aware of the facts. And I believe with such a show, you are actually presenting the facts and, you know, giving out or spreading the knowledge out there. So that is why I say this is a wonderful way of disseminating knowledge out.
That brings us to the close of part 1 of this episode of Let's Talk Concrete. Today we have explored how concrete has evolved from conventional mixed philosophies to high-grade and high-performance materials that are redefining strength, durability, and design thinking. Dr. Jain has helped us understand why this shift became necessary and the engineering challenges that come with designing such advanced concretes. But this is only half of the story. In part 2, we will go deeper into real-world applications, economic feasibility, and how technologies like these are pushing the boundaries of what structures can achieve. So stay tuned for part 2 of this conversation, where we translate performance into practice and design innovation into project reality. Thank you for watching Let's Talk Concrete. See you in the next part.